Thanks. Okay, so I'm Ben. I'm Cuba on Twitter. I'm from the University of West of England. I'm an associate professor in computer science. And well, I won't go too much into me. I'm going to talk about Rust, obviously, tonight, and I'm really into Rust. I wouldn't claim to be an expert in Rust. I suppose I'd probably claim to be an expert in Haskell or C++, my dreaded C++. But I am really interested in Rust, and it definitely has many benefits, bringing the things I suppose I do like about C++ and Haskell together. And so I'm going to talk a bit about what I've been doing with that since lockdown, actually, one way or another. And in particular, I do quite a lot of research and work that involves audio, in particular musical instrument design. As I was saying before the call, a lot of it's around embedded systems. But I haven't had access to my research lab or my soldering irons and those sorts of things. And so I haven't done much of that during lockdown. And actually sorry, I'm on the wrong, click on that. And I should just say, yeah, all the material from this talk, including all the source code from the available things I talk about. I'm not going to show that much source code today, but all the projects on my GitHub, it's all downloadable, accessible to slides. And there's an up and coming paper, which is going to be at the Faust conference, which describes quite a bit of this work and a bit more. Okay, so what's not in that paper is kind of how this kind of work came about. And I suppose why I started looking at it. I mean, I was already doing a lot of stuff with Rust, but again, mostly on embedded hardwares. But I also teach computer science. So in particular, I teach first year and second year programming, which is C++. Going to be teaching a third year module in Rust, but not until next year. But at the moment, it's C++. And normally, we expect most of our students to come into the labs. We can't require that they have very powerful machines. And some of them literally turn up with iPads. They're doing a computer science degree and don't have any kind of laptop or even a computer at home. And so they do a lot of their programming and so forth in the labs at the university. Of course, with COVID, that's all gone out the window. And so I've designed for our programming course this year, we're just using Azure and we're going to run it. And it's just very simple, it's just a LAMP-based stack, which is running a server and everything. But one of the things I teach is graphics. They do simple, 2D based graphics. And clearly, if they're just using SSH, even with remote extensions with Visual Studio Code on the client, then they couldn't do graphics across the terminal. So I had to come up with an alternative solution. Turns out there already exists a really nice solution with a bit of hokey pokery and CGI scripts to make the things get publicly available in their public HTML directories. We can use JavaScript, and in particular, we can use WebAssembly, which is a low-level virtual machine that can run inside the browser. I'll talk a little bit more about that in a second. But particularly, one of the nice things about it is that it already supports OpenWebGL and STL. So I could embed all that. The students didn't need to worry about that. They could all just program remotely, or actually locally via a client, which is Visual Studio Code taught remotely. And then everything would just happen automatically with a bunch of simple Python scripts that would copy everything. Then they'd go to the HTML page and bang, they'd have their applications running and we'd be able to mark them and see them. So this is not what this talk's about, except for WebAssembly. I just wanted to see that. So I got thinking about that. And WebAssembly is this amazing thing. I know that you've had one last month, so I'm not going to go into a lot of detail about this, but just to recap, it's this a binary instruction format, which just describes a stack-based virtual machine, in some ways similar to Java, in some ways not. And it provides certain security guarantees. And what's really nice about it is that it can be targeted from system-based programming languages. It doesn't just have to be JavaScript or managed languages. It works pretty well. And at the moment works best for kind of the system throw languages, including C++, which originally was its target, but also Rust, because Rust compiles very well to it. And so that kind of got me thinking, got me wondering, what else could I do with that? I can't get into the lab. How could I tie in my other interests around designing audio instruments and musical instruments for embedded systems, but also on desktop systems? And so it got me wondering. And it turns out that WASM's not limited to the browser. Hopefully you discussed this a little bit last week. You know, it's not needed at all. There's no reason why it would be. But most importantly, there are a number of really excellent projects that are looking to run WASM. I put natively, it should probably be in quotes, because obviously it's not, it's translating it on the fly using JIT technologies to run it natively on, you know, x86, ARM. But also what was really interesting to me, and I'm not going to talk that much about in this talk, but it's something that I've started to look at, is that it's possible to run these things on embedded devices. Whilst people have tried to run things like JavaScript on, you know, let's just say an Arduino compatible kind of controller, they haven't really been that successful because of the garbage collection is pretty expensive, and you know, you quickly run out of very limited resources. Where it looks that WASM is actually quite viable on embedded platforms. I mean, there's still a performance degradation, but maybe it's manageable. And so that's really exciting and really interesting. For the time being, I've really focused on these top two here, which is one is called WASM Time, which was, as I'm sure many of you have seen, was developed at Mozilla mainly, but of course, due to the layoffs, quite a lot of that team is now gone. I don't know where they're going to. And then WASMA is a more industry-focused consortium that's been developed as well. And Life is these ones are interesting for me because they're both written in Rust. So that's what drew me to them. There's another one called Life, which is actually highly performant, but it's written in C++. And so actually, I think it might be written in C. So it's been a bit less of interest to me. There's also another really interesting tool that has come out of that, which is called WASM to C, which takes a WASM binary and translates it to what Alon Zaki, I'm not sure that's how you pronounce it, but he is the person who did Inscription originally, and which is the C++ originally to JavaScript, or to asm.js, as many of you I'm sure will be aware. And he's got this really interesting talk that I saw about the 2nd of April, I think it was. I couldn't find the exact date, but he tweeted about it, which talks about this WebAssembly and the elusive universal binary. So the idea that WebAssembly could be a format that we could use for all platforms, you know, that so it wouldn't just be, it'll be compiled once, but run everywhere, potentially. And that was really interesting. And he was using WASM to C because at that time, the other ones I've mentioned, WASM Time and WASM, were not quite ready for wide use on multiple platforms. So that's kind of got me thinking, got me started, and I highly recommend going to look at this presentation. It's a really great presentation, and he's got some nice benchmarks in there to give you some ideas about where it is at this point. But, you know, is it possible really that WASM could imply that we could compile once and run anywhere? And, you know, we've heard that with Java, we've heard that with C#, and I'm sure that we heard it with Lisp, you know, when McCarthy was defining that. And it's been a goal of computer scientists for a long time. And I'm going to be straight up with you straight away. I'm not proposing anything like that. I'm not, you know, going to try and change the world or anything. I'm much more in the favor of this quote from Tiffany Aiken, who's a character from Discworld. And she said that things would be different one day, but you had to start small, like oak trees. And that's what I'm doing here. I'm starting very small. I'm just a little dot in a big haystack. Okay, I don't want to propose anything, but it's an interesting area, I think, and WASM and Rust are really good friends, and it makes an interesting place to research. So during that time, this is what I developed, and I mean, this is just a picture of it, but this is the VL1 from the Casio. It was my first musical instrument when I was a child, and it's one I purchased recently on eBay. And over here is a software emulation of it, which is written in Faust and then compiled to WebAssembly. I'll talk about what Faust is in a little bit, but basically it's a DSP-based language. And it's written in, it compiles from Faust to Rust to WebAssembly. And then this application here is just loads WebAssembly. It can load any kind of audio unit. And that audio unit is just compiled once. This application is compiled once for a platform, but the WebAssembly itself is compiled once for all the platforms that this application runs on. And what's really exciting about this, because on the left-hand side, this is a Aerosmith's Daisy, which is a STM microcontroller plus a 24-bit DAC or ADC, sorry, what am I saying? For doing audio, and it has 8 megabytes, I think, of off-chip memory and about 1 megabyte of on-chip memory. But what's really cool is that the WASM that I'm talking about running in this one on the right here also runs in this one here. And I haven't got it here tonight, it's downstairs. I didn't want to risk doing a live demo of it. I'm always a bit nervous of that. But we've hacked this by connecting to the keyboard matrix and directly to the Daisy. And you can play the VL1, but play the faust to WASM simulation running on the Daisy. And it all works and it's exactly the same WASM Pro that runs in this one on the right. So, and I'm not trying to claim that this would work for every piece of complex code, because obviously the VL1 is actually not a very complex chip to emulate. And so it doesn't need that much horsepower, but all the same, you can add a reverb and another bunch of effects on here and it'll run quite nicely, but you compile it once and it will run anywhere. So that was the kind of goal and inspiration. So this is captured in this picture diagrammatically. I've got a .dsp, as I'll talk about in a second, which is basically just a signal processing code, in this time written in Faust, but it doesn't need to be. We compile it once to WASM compared to the n times you'd have to do it if you were compiling it for each of these different architectures to make it work for Windows, Mac OS, Linux, even though they're running the same x86 or ARM processors underneath. You have to tie it to the particular architecture you're compiling it for, operating system. And of course, we'd have to compile even again differently for bare metal. And that comes with a bunch of constraints because you don't get the standard library and things like that in the same way that you would on these OSs on the left. So that was a goal, and really the rest of the talk is just kind of talking a little bit about the work that I've done to make that happen so far. And in particular, I wanted to make it as portable as possible. And so I defined this thing called an Audio Anywhere module. And an Audio Anywhere module is made up of the WebAssembly, which is compiled once and completely portable. And because, as I'm sure you're all aware, interfaces are a real pain across getting it portable across OSs. For desktop applications, the interface is written in HTML. There's nothing special here. It's just purely HTML. It's using WebKit and things like that, so that we can evoke and call it into the Rust code that's running the WASM code. But it's nothing, it's just very basic HTML with some CSS and some JavaScript. I don't claim anything. I'm neither an expert in this area or to be honest, is anything that much is not that needed, other than passing information between the Rust application that's running the virtual machine for the WASM and back up to HTML and so on. That's the only complicated bit, but standard, fairly straightforward protocols. Once you get it into the Rust code, I'm communicating it around the system with channels, and so it's not a big complicated system by any means. But it's very convenient. It works really well. It's completely portable. There's no OS-based code in there and stuff, so it runs on all platforms except for the embedded platform. The embedded platform has to have a completely different library for interfaces because they're actual physical buttons and things like that. And so there, it's calling down to some C++ code that's doing PWM or turning some switches on and off or reading a pottometer and so forth. And again, I'm not going to talk too much about that in this talk. Okay, so really a hosting application, which is written once. It is important, I think, to note that the hosting application, obviously you have to write this hosting application, which is the one that had the software synth loaded into it on the previous slide. But you only write that once or compile it once for each platform. And you never have to recompile it again. You release it once, they install it, and then the WASM code is loaded dynamically to actually run the different audio plugins. So that application that I showed you can run all different sorts of plugins, and they just pop in and load into the same application. So the nice thing about that means that you could serve all of your WASM code and your interface code via a web server, say, for example, and then the single app that was installed once would load and allow you to select between those different things. There's no having to cross-compile it for different architectures and that sort of thing. And it's a very straightforward setup here. I mean, this is only a subset of it, obviously, but the WASM code itself is an array of WASM files, and it's an array because an audio graph is composed of different nodes where audio flows between one node to another node. So it could be a generator, such as like a synthesizer going into an effect like a reverb or something like that. And so you can build up complex audio graphs. And so we've got array. There's only one GUI for the whole thing. And obviously you need to know how many inputs and how many outputs you've got for your graph and so forth and things like that. But again, not that complex really. So we've moved away from our compile many times to our compile once now. And here we'll give you an idea of how the system that I've developed works, is that we start off with some DSP code at the top here. Again, this could be Rust code, could be C++ code, or whatever. In my case, it's Faust code, because as I'll show you in a second, it's a very nice, concise functional programming language for expressing audio or signal graphs or signal processors, as it calls it. And the nice thing about it was I was started from a compiler. I've modified the compiler, but I started from the compiler. Stefan is on the call here, who's one of the key developers of that compiler, the Faust compiler, that already had a Rust backend. So it generated Rust. It also generates C++, also generates native code in some cases, I think. I don't know, Stefan would have to tell you about that. But for me, I was interested in going to Rust, and I'll talk about why that was in a second. And we compile to WASM. We have our interface that's written, and these two are just bundled up together, and then they are shipped just once to all the different platforms. And this is the kind of standalone application that runs here on the different platforms that are compiled once. And so the idea is that, you know, you are literally compiling these things once, and then you never have to do that again, and you get cross portability to these different platforms. Okay, I've already described. I'm going to skip from that one a little bit, I think. Okay, so there's an API that you have to adhere to, obviously, because to make these modules loadable. And I'm going to talk briefly about what the API looks like. So whenever you load a WASM module, you need to be able to initialize it. It's an audio module, so we probably want to know the sample rate. And if the sample rate changes, the module needs to be reloaded because there's some internal optimizations that depend on the sample rate. And there's a bunch of functions for getting the sample rate, even once it's been set. There's also some things for getting how many inputs, how many outputs there are. And also where, if it's polyphonic, i.e. has more than one musical voice, not just mono, then you need to know how many voices there are. And that's so that we can handle MIDI messages and things coming in. But also there's some allocation that goes on. I mean, nothing surprising. If you were to look at the Faust API that it generates things very similar to this. Again, I'm not claiming any novelty there. There's functions to set the indexes. So these are like parameters. You know, there's things like you might want to change the gain, for example, or the volume on a particular signal, for example. And these are set here. For anyone who knows about WebAssembly is all integer-based for inputs and outputs, and so the parameters are not named; they're done by index and so forth. Which of course has the benefit of being much more formal. We don't really want to pass strings around and things like that. It's much more harder to optimize. We have the ability, if we're talking about musical instruments, particularly synthesizers, then we want the ability to play musical notes. You know, to play a note with a certain pitch, at a certain velocity, for example. So we have functions to handle note on, note off, no surprise with those sorts of things. MIDI is the obvious one to support, but we also support OSC, and where strings do come in, and actually started to work on MIDI 2.0, but which allows more interesting kind of continuous note playing and things. But again, fairly straightforward. So the big interesting thing here is there's a function that computes an audio for a number of frames, i.e. a buffer size. So maybe I want you to compute 64 samples, which is what I do run at most of my tests. Depends on the latency of your audio hardware, and obviously how much compute you're doing, because you need to be able to handle some buffering, because otherwise you might get dropouts and start getting glitches and things like that. But again, these are not things. So I'm not going to go into a lot of detail about this, but there are some things here. I'll just quickly, I don't know if I ever like highlighting things like that, but to make this all work smoothly in the WebAssembler code, we need to be able to map the input and output buffers that are inside the WebAssembly address space, which is isolated in general from the CPU address space or from another WebAssembly node within the, well, at least the way that it's initially implemented. And so to make those visible to the outside world, we effectively need to memory map them at times. Now, of course, we don't have pointers in WebAssembly. We have integer offsets because it's just like a linear array. And so we need to get those offsets back and then map them in the CPU world or in the host world into effectively a pointer, you know, and so we have functions inside the WebAssembly that returns the offset to the known buffer array for the WebAssembly. And then what we do outside is that we know where that buffer array has been placed in physical memory. So we can then add that to a real offset and get the actual location of the input and output buffers for the audio graph. And I'm not going to talk too much about that today, but actually there are some really interesting optimizations that can be done around that because the WebAssembly is being compiled on the fly as you load it. You can actually do some quite interesting, if you're willing to modify the JIT compiler for the WebAssembler, you can actually do some interesting optimizations around this, particularly because, as I'll show in a minute, all of the input output buffers are known statically. We know how many there are, so we can do some interesting optimizations at load time. Okay, so the as I said, for me, writing audio components is, so this is a matter of writing the signal graph, the DSP part of the application. And for me, I quite often use the functional programming language called Faust, which was developed at Gram in France. And Stefan is one of the key developers. He's on the line today. And it's a domain-specific language, purely functional for implementing signal graphs. And I quite like it because I come from the Haskell, so I like functional programming. But actually, if you're familiar with DSP, it's nice because it actually is a very close representation of the signal graphs that you would have learned when you did your signal processing. And so it doesn't have all the overhead and the kind of noise that if you wrote this in C++, you know. And it turns out, because Stefan and others are very smart at doing optimizations for a domain-specific language, it can actually generate incredibly efficient C++ or Rust code. And so you don't have the overhead that you might have from using a higher level language in some cases. And so it's actually incredibly powerful. This isn't really a talk about Faust. And as you'll see in a minute, it's not necessary, it's just used. But here's an example of Faust itself. And you can see here that it has some things to make it convenient. So H sliders and things like this are basically describing inputs and outputs. So things that are low rate. So what I mean by that, they're not running at audio rate. They're more likely running it at 10 hertz or something like that, you know, where you're twisting a knob or you're pressing a button and things like that. These allow you to have inputs and outputs that change the frequency in this case, or the gain in this case. This is a simple sawtooth oscillator, and which is built into the Faust standard library, not something that I've written. And there's a couple of little extensions that I've added to the Faust compiler, which I won't talk about in detail, but allows you to describe how many voices you want. So whether it's polyphonic or monophonic, and in this case, I'm using two voices. So you can play two notes at the same time. And if you press 3 notes, then one note won't get played. But if you're playing 2 notes and you press a new note, one note will be stolen and will be replaced with the new note. So the oldest one is just a simple, so things like that. And obviously, in general, you might want to have more than 2 notes, because if you're playing a chord or something, you want to have at least 3, potentially probably 6 voices as a minimum. But this is just a simple example. And again, you don't really need to understand this code for this talk. I just wanted to put this up. This is what I talk about, just as a way of getting it going. Mike, how long have I got left?
You've probably got about 10, 15 minutes.
Okay, brilliant. Okay, so I'll talk a little bit about the implementation then. So compilation flow for audio anywhere is with the DSP code. So this is the actual taking the signal code and creating it to WASM. I'm not going to talk about the GUI code because, like I said, that's just fairly standard HTML5, nothing smart. To be honest, I'm probably the worst HTML5 programmer on the call, I guess. But anyway, there's nothing interesting there. Other than that, I only use really pure JavaScript. I hate all those frameworks, but that's just me. What you can see is that we just want to generate some WebAssembly at the bottom here. So any language that can compile to WebAssembly, literally any language, can be used to write audio anywhere DSP code, long as it implements that API that I talked about previously. So you could write Rust modules. I've written a couple, just very simple ones. You could write them in C++. I haven't done that. I try not to write C++ unless I have to. And you can write Faust, because Faust can be compiled to Rust or C++, which can then be compiled to WebAssembly. And Stefan will tell you that there's also a WebAssembly backend for Faust, but it has a slightly different ABI and a different representation for the API, so it would be difficult to match that directly. And so I focused on Faust, but not for any other reason than I just found it simpler and easier. But I did also want to go via Rust. That was very important. That would become relevant, and I'll point out in a second why that was. And then I compile it down here. The Rust compiler compiles it to WebAssembly and out the back here. Straightforward stuff. I'm not using WASM pack or anything like that. It's just straight WASM code, and then I use WASM opt and things like that just to optimize the WASM code. But that's all separate WASM code tools. And once you've got that, clearly it can be run on these different architectures, as long as you've got a virtual machine or a way of taking your WASM file and running it on these different architectures. Which, one of the really nice things about WebAssembly, just an aside, is that because it's 32-bit at the moment, it's going to 64-bit, that they haven't been that much support on the ARM architectures, particularly the Raspberry Pi, which I'm quite interested in because you can get some quite nice work going on there for audio. Until recently, that they ported the new Raspberry Pi 4 has the 64-bit kernels, and so all the virtual machines are mostly require 64 bits, but they're running now on the ARM architectures as well, not just the embedded architectures, but the the application processors too. So static memory for the module is laid out fairly much as you'd expect. This is all generated at the point where the DSP code's thing. So all of these inputs and outputs are generated with respect to the number of buffers or audio buffers coming in and out of the graph or of a module. That that we don't generate 10 of them, or sorry, 12 of them, for 12 channels or something like that, or 6 channels, I suppose. They are generated specific to each piece of DSP or Faust code, because how many inputs and outputs there will be at compile time. And they're just, standard buffers. Rust is not too friendly with having global memory. As I'm sure you all know, you have to end up using unsafe and things like that for these. And I've actually don't do this anymore, but in the work I've done today, I'm just going to talk about that, which uses these static buffers. And I have a static instance of this DSP or engine code here, which I'm going to talk about in more detail. So why do I compile to Faust? Well, to Rust. Well, really, for me, it got me started because, well, one, I'm quite into Rust, and two, because Rust is a very close friend to WASM. Lots of the tools, documentation, everything are really closely integrated, often developed by the same group of core people. And but there is another key reason, and is that if you're careful with your Rust code, particularly if you use zippers and things like that and iterators over your arrays, you can avoid all the horrendous bounds checking. Once you've avoided that horrendous bounds checking, you'll actually find that the auto vectorizer for LLVM works really quite well in many cases. Of course, because we've zipped them and everything, we'll know that we won't be going out of range and things like that. So it doesn't have to have a lot of those things that he would even still have to put in cases in C++ code as well. So it's quite nice. WASM, not WASM MVP, the the viable product one, but the extensions to WASM have 128-bit SIMD support as well. And so we can, with the auto vectorization turned on, we can make use of the WASM SIMD code as well, which has been a real blessing. As you'll see, I'll give a couple of little examples. And I wrote all the supporting libraries in Rust, and so it just made it nice and compatible, but not for any other reason than that. Okay, so I've got this tool, which is a modification of the Faust compiler that compiles a Faust DSP file and generates a WASM file. It's a fork of the Faust compiler. You can find it on my GitHub. And it generates code that looks like this, which is fairly similar to the code that's generated by the Faust compiler for Rust anyway, with a couple of differences. In particular, the compute function that Faust generates, this is the standard entry function for Faust code, has here, I've fixed the size of the inputs and output buffers. I know the size because I know those. And so these are slices of fixed sizes, which is quite important because it means that we can use fixed pattern matching to unpack these buffers into slices that can then be zipped. And that's really important for the auto vectorizer, but not, I mean, you can still do it with the auto vectorizer, but it ends up with panic code having to be included. So the WASM file generates it because, you know, you can't know for guarantee that the arrays will be the right size, those sorts of things. So, and it does make quite a lot of difference, particularly if you want to run on an embedded platform. And I couldn't get it to fit until I did this optimization. And so it turned out to be quite important. And there's really no reason for not doing it because we know it. We know how many inputs and outputs there are. So it's important. So I've ended up having this separate external compute function because we're calling it from the outside world. This is a function that actually gets called. I mean, it doesn't, it gets called from the API, but effectively it's being called from the non-WASM world. And we can't pass pointers in. We can't pass arrays into that world. We can only pass integers. We can't pass offsets to outside worlds either because we don't have any. Now, there are extensions to WASM, but I don't use that. So all we're passing in here is the number of frames, i.e. the number of samples to generate, and everything's handled internally and then memory mapped externally to get the input and output from the graph. This is what that function ends up looking like. It's just simply constructing some slices of sample size from the outputs that we knew about, you know, the output arrays that we generated previously, that are statically known and statically allocated. It has to be unsafe because we can't access the outputs because they're statically generated. But other than that, it's safe. But that, and then we just call the compute function with a fixed sized array here. And that's really nice because this is just a subset of the full compute function, but it is still the compute function for in here. And you can see that we can unpack the outputs here using a fixed sized array because we know that this is a size 2, so we can pattern match against a 2. This is all automatically generated. None of this code's written by hand. It's generated from the Faust code, but it knows how many inputs, outputs, so it can generate the correct pattern matching. Doesn't have to use the comma ... for example, to handle things where you'd end up having to have a panic code in there and all that sort of stuff. So it works really well. And once we've unpacked them, of course, we can create iterators for them. And then most importantly, we can zip them to give us the code that can then be optimized by LLVM. Again, I think this is it was actually quite hard to find, but it's fairly well known to the Rust community. This is not me coming up with some idea, you know, or optimizing it. This is, you know, if you go, after a bit of Googling, I managed to find it. You know, it seemed to be hidden down on some forum somewhere. I couldn't find anywhere that's written up. So if anyone knows if this is actually, approach has been written up and documented, but it just seems to be one of these things that most people in the Rust community know, and you don't know it, and then one day you know it, and then you're like everyone else in the Rust community, maybe, I don't know. That's what it felt like to me. It was slightly frustrating because, you know, it took a little while to find it, but then you find it and you're like, oh yeah, and that was obvious. But anyway, maybe that's just me, I don't know. Anyway, I'll move on. So there are a bunch of other things that are really interesting. I talk about those in the paper, particularly about how you handle stitching the graph together, because of unfortunately WASM doesn't support shared libraries, which is really annoying. And there's no way of linking shared libraries, so you can't generate relocatable code. Now, again, you'll find on the forum some people have managed to do it, but it is a nightmare because LLVM doesn't generate the offset instructions correctly for in general for WASM code. I don't know why it would just be generic, but it's not. And I think we'll get there with that, but we don't have that yet. So you kind of have to unwind that, remove all the static, used a singly shared allocator, and then you can cheat by using, well, I don't know if it's a cheat, but the threading extension that they've added has a shared memory, and you can share that between all your WASM modules. But again, that's quite, and it's quite a lot of complicated code. I had to modify WASM time because it crashed. And so I haven't presented that here, and it's not public yet because I got to be, it's a shoestring implementation at the moment, but it proved to myself that it's possible. But anyway, I'll just conclude quickly with how this all works in practice. So the C++ Faust code, Faust compiled to C++, optimized Clang code at 03 with auto vectorization turned on and so on and so on. And you can get some really quite good speeds as you would expect going through. This is not WASM code. This is just straight C++ code, checking how well the optimizations that I've done and some other people have done. Blue Note in particular from GitHub has done a very similar thing. And Stefan has been implementing that. And this was the original Rust compiler, Faust to Rust compiler, which is about 20 times slower than the C++. But when we applied the optimizations that I did and Blue Note had done as well, we can see that it's slightly faster than the C++ code. I'm sure if I ran this 20 times, they probably wouldn't be any faster. You know, I'm not claiming at all. It's going through the same compiler. It's applying the same auto vectorization optimizations on code that's very well structured. So, you know, there's no loop carry dependencies or anything like that. So it's fairly straightforward for LLVM to optimize for SIMD. But it's really good because now we see that actually in this case, Rust is competitive with C++. You know, I haven't done an extensive benchmark suites and anything, but it gave me the confidence to feel that we could go on. And okay, so the next couple of slides just show some very early benchmarking done for WASM code, calling into WASM code. And this is just an empty function. So this is the cost of a function call, effectively, you know, calling into call. And you can see that on x86 on my Mac, it's just a Mac, nothing else was running, but it's, you know, it's a high-end i9 Mac. If you run that natively, there is effectively zero cost for a function call. It's pretty impressive. You know, even today, that's pretty zero cost. But we're talking about microseconds here. So even for WASM, it's pretty small. And one thing that's interesting to note that this is the WASM time runtime, which is the one that I ended up using almost exclusively because it's the only one that supports WASM 128 SIMD and not core dump. WASM says it does, but I just couldn't get it to work properly. But WASM in the case of the null function is slightly faster. I mean, not a huge amount, you know, it's 1 microsecond of 0.7. So, you know, it's not a huge amount of difference. But what's quite interesting is that as soon as we start doing computation, so this is running a sine oscillator and it's a block size here of going from 0 to 2048 of different sizes. So running for 100,000 iterations for each time. Again, we're still in the microseconds here, but you can see that actually WASM time is actually pretty nice. You know, it is slower than the native code, but not hugely. And, you know, we're only using a straightforward JIT. I'm not using any of the LLVM based JITs or anything like that. It's using crane time, I think is that what it's called. I can't remember now. But anyway, so it's a fairly, I mean, it's a 2-pass JIT. So it's still doing quite a lot of optimization, but it's nowhere near the kind of optimizations that LLVM would be doing. And you can see for some reason, and I have no idea why, the WASM time, the WASM runtime, which is this green one here, is starting to go a little bit off the ball and falls off quite quickly. I don't know why that is. I've been in communication with the WASM people, but we haven't narrowed it down yet. And I have to be honest, I haven't spent a lot of time trying to work that out. But it made me feel a little bit happier because the WASM time runtime seems fairly consistent. Doesn't seem to be falling off or getting worse. You know, it's slower, but if you look, it's slightly losing speed against the native, but not a lot, no more than you might expect. And then this is a copy in and out. So this is going from inside, sorry, it's going from outside the WASM world into the WASM world and back out again. So it's copying all the data in and out. And as you'd expect, if we're doing that on a native, it would be pretty, there's not a lot of cost. We're only copying 248 bytes at max. So we're not copying loads of bytes. And this one is WASM time. This is running with SIMD, so there's no WASM one. And it's definitely slower, but we're still in the microseconds, nothing to worry about. And clearly, there will be a cost to this, but what's important about this graph is that this cost is only on entry to the graph and on exit to the graph. The rest of the time, all the DSP code, even if you've got multiple nodes in that graph, which are separate WASM files, there's no copying going on because we're indexing into shared memory that's shared with inside the WASM space, address space. So, you know, the only copies that are going on are values being generated and copied into new channels and so forth. There's no data movement in the way. So as soon as your graph gets any kind of complexity, the likelihood you're not going to see this overhead at all. You know, you're not going to be, you know, if you imagine that you're running a buffer size of 64 or even 128, it's going to be fairly negligible to the amount of compute that you would be doing. So it's actually pretty good. You know, I was quite pleased with what we were seeing. Okay, and I think mostly that's all I had to say. I've already mentioned it a bit. The lack of relocatable code in WASM is a real bind because it means we can't do the simple approach of handling things like having statics for each module and then just setting up offsets into them. And so the way I've got around that is using wealloc and just actually dynamically allocating everything and on as things are instantiated at the beginning when the graph is initialized. The downside of that, and I think it is quite a big downside, is that the API can no longer be the simple one that I showed you. We have to start passing handles around. So if you've ever used OpenGL or OpenCL or something like that, where you basically get an allocation back and you get back a handle to that, you know, an abstract thing, we have to do that for all our allocations that are externally visible to the outside world because everything's in a managed heap now and not statically allocated. So it makes the API more complex. Of course, it makes the API more flexible, but it also makes it more complex. Anyway, I've probably talked way too long and too much. So you can find out lots more information on the project website. And yeah.
Thanks for that, Bennett.
Thanks.